Right triangles like this one are one of the most important shapes in geometry. And this triangle is the foundation of one of the most important theorems in mathematics called the Pythagorean Theorem. The Pythagorean Theorem didn't actually start with Pythagoras. It actually started with the Babylonians and the Egyptians who used this to build things like these pyramids here. And they had a really amazing technique that they used to build these wonders of the world here. And we have some evidence that they used ropes to make right triangles, specifically 3, 4, 5 right triangles to make perfect right angles. So Pythagoras came along a while later. He was about 500 BC, and the Pythagoreans were geometers. The geometry that they studied was the foundation for everything that they did in mathematics. They didn't do a lot of algebra, they did a lot of geometry. And so they took this triangle here and they studied the squares. If they put a square on the bottom here and the square on this side, and then a square on the hypotenuse here, and they said, what is the relationship between those squares? And they found out that the two smaller squares have an area that adds up to the area of the large square. And that was the key to opening up a lot of applications and discoveries that could be made with the Pythagorean theorem. These two squares, the a squared and the b squared, equal the c squared in area. And so now we can take that on to algebra, which leads us into calculus and lots of amazing tools and things that we can develop with the Pythagorean theorem. Let's look into that.
So the Pythagorean theorem really was a geometry theorem. We're talking about these areas of these two small squares of this right triangle add up to the area of the square on the hypotenuse. So that's the original form of the Pythagorean theorem. It says the area of the squares of the two small sides, the legs. By the way, these are called legs. That's important. We have legs, two legs, the two sides that make the right angle. And then we have this side, which has a fun name, the hypotenuse. Hypotenuse. All right. So the hypotenuse is that third side that's opposite of the right angle. Okay. And so we usually call that hypotenuse C and A and B for the shorter ones there. And we come up with this theorem here, this equation that tells us a squared plus b squared has to equal c squared. So the squares on the legs have to add up to the square on the hypotenuse. So we can look at a couple examples here. We can answer this kind of question. Let's use the Pythagorean theorem to determine if this is a right triangle. So we've got 3, 4, and 5. We don't know if it's a right triangle. Well, if it was, then it would have to follow the equation a squared plus b squared equals c squared. And in fact, we'll put a little question mark over that equals because I don't know. Well, what is a and b? Well, a is, maybe we'll call that 3 squared. B is be the 4. The most important part is that the c would have to be the hypotenuse. And let's see if that's a true statement. Is 9 plus 16 equal to 25? I think it is. Both sides come out to be 25. So yes, it's a right triangle. Remember, a right triangle has one right angle. Okay? So it's a right triangle. All right. Cool. Well, we can also use it to find a missing side. So we have our A, B, and C. We've got our formula, and maybe we'll call these A, B, and call this side C. And so we've got 9 squared plus 12 squared equals x squared. And this comes out nicely. 144. Yep. And this gives us 225, and the opposite of squaring, we got a squared here. The opposite of squaring, we got a square root, right? So let's square root both sides, and we've got our 15. All right. So many of you probably have some experience with this, so hopefully this is just a refresher. Well, what if we're missing one of the legs? Well, same story. Make sure you start with the formula, a squared plus b squared equals c squared, and then we could put the x in there. I guess you could have left it as a if you want. And then we can go from here. A little twist, we're going to have to subtract. You see that? Got to get that 64 out of there. So we get that 64 out of there. We get 36. And what's that last step? That last step is going to be to square root. So x is 6. All right, now these, by the way, these are called Pythagorean triples. These are special ones. 9, 12, and this came out to be 15. This is 6, 8, and 10. They will not always come out to be perfect whole numbers there. So sometimes they'll be square roots. A lot of the time they'll be square roots. But if they are whole numbers, then we call these Pythagorean triples. So that set of three numbers, 6, 8, 10, and 9, 12, 15 is our Pythagorean triples. Well, along came a guy named Rene Descartes. And Rene Descartes is responsible for developing our coordinate plane that we use all the time in algebra. And what Rene Descartes did was he took these ideas of geometry and algebra and put them together. And we have what we call analytic geometry. So analytic geometry allowed us to take some figures, put them in the coordinate plane with x and y coordinates, and figure out some important or useful properties about them. So we're familiar with the fact that coordinates are the x-coordinate first, the horizontal, and the y-coordinate second. So we have some points here. And so sometimes it's useful to think of these as generic points. We'll call these x1, y1, which just means the first x and the first y, x2 and y2, the second y and the second x there. And we want to figure out what this length is here. So it's slanted. We can't just count. We can't say, well, this is like 1 unit, and there's like another, and there's another, and, well, these jumps that you can see that I'm doing, those aren't even equal jumps. So we can't count when it's slanted like this. Now, if we have a line that's horizontal like this, there's a horizontal line. We can count that one. That's 4 units, right? 4 spaces. We can count a line like this. That is, what, 6 spaces. All right, in this case. So what if we had a farther distance? Could we figure out what this is? Now this over here is at x2, and this is at x1, all right? So let's make this generic, keep this general. Let's pretend that it's actually not really 4. But how would we get that distance? Well, we could take whatever this is and we could subtract them. See that? We could take the x2 distance and subtract the x1, and that'll tell us how far it is between these 2 points. And if this height up here is at y2, and this height down here, the height of it, remember the y value is the height, how far apart are these 2 things? Well, again, let's pretend like this is general. Let's ignore that 6, because these points could be all over the place. So this is y2 minus y1. So that's the vertical distance and the horizontal distance. Well, if we want to find this distance here, let me call this d, or maybe a little better for using our geometry. If this is point A down here and this is point B, then the length of this is AB. That's the length of this line. Well, according to the Pythagorean theorem, if we take the x2 minus x1, That's just the length of this line, this leg, and we square that, and we add the y2 plus minus y1. That's the length of this other one, so I square this, square that. That's got to equal AB squared, right? AB squared. Now, what if I want to figure out the length of AB? Well, I could get rid of that square by square rooting, right? And remember, what you do to one side, you got to do to the other. So that leaves us, we'll come over here, with this very useful fact that the square root of x2 minus x1 squared plus y2 minus y1 squared is going to be the length of AB. There is our distance formula. So, how do we use that distance formula? Well, let's say we do have specific points. Let's go ahead now and let's come back here. Let's say that we are 2 points that we're using are 3, 2, and this point over here, let's say that looks like it's 7, and 1, 2, 3, 4, 5, 6, 7, 8. Okay, 7, 8. Well, we could draw a right triangle, and we will do that often. We can draw a right triangle and use the Pythagorean theorem. That totally works. But let's see if this new tool works. So this is our x1, y1, and our x2, y2. And let's plug that in and see what we got. So the square root of, let's subtract the x's, 7 minus 3 squared. Subtract the y's, it says. Put the y's in there. And so we've got 8 minus 2. And that's going to give us our length. So let's do some math. This is 4 squared, which is 16. So we got the square root of 16 plus this guy gives us 6 squared, which is 36. And so that's going to be AB. And 36 and 16 is going to give us 52. And 52 is not a perfect square, so we will leave it alone. That is our answer. So, Pythagorean theorem can be changed into this. When you look at this, remember, this is just like a squared, this is just like b squared, and our c squared, but the squared has turned into a square root. All right? So that's just the Pythagorean theorem, what we call the distance formula. So there you have it. So the Pythagorean theorem came all the way from Babylon and Egypt, all the way through the Greeks and Pythagoras, who figured a whole bunch out, to Descartes, who gave us our distance formula. And now we can apply that in lots of different ways to mathematics.